Okay, good afternoon and welcome to everybody for this session on Heat and Mass Transfer 2. We have four speakers. The first one is pre-recorded. It's Dr. Tom Flint from the University of Manchester. So he's unable to be with us, but he's provided us with a recording. So can we take that off? Can we start that, please?
Hi everyone, my name is Dr. Tom Flint and I'm going to be giving a talk today. So first of all, I'd like to apologise for not being able to be there in person. Certainly at the start when I was due to give this talk. I might be able to make the session later, but my colleague Galvin Paravenden's there and we've worked together on this presentation, so he'll be able to answer any questions that you might have. And also, like I say, I should be there to be able to answer any questions in the text later on. So what I'm going to be talking about today is different approaches for simulating advanced manufacturing processes. So an approach we developed at Manchester and an approach developed at University College Dublin. Both approaches have pros and cons. We'll discuss those. First of all, though, I think it's important to say why we are interested in modelling advanced manufacturing processes where we have vaporization. And the reason is, in a nutshell, that if we can join metallic components using power beam welding processes, we can get a step change in the construction economics of large capital expenditure projects like nuclear reactors, fission and fusion. And also we can understand sort of novel technologies like additive manufacturing, powder bed fusion processes better, because the vaporization becomes quite important in those processes. Furthermore, if we're interested in understanding how things like preferential element evaporation occurs in these power beam processes, as being shown here, we need to understand these vaporization dynamics of the liquid metals. So, and the reason that we want to model is because these phenomena occur in incredibly short time scales. So the time over which a thermocapillary, which is the vaporized section through an electron beam or power beam weld, collapses is of the order of 10 microseconds, so very difficult to observe experimentally. So the two approaches that we're going to be discussing then, the two approaches we're going to be comparing, is the approach at Manchester, as I've said, where we explicitly account for the transition between condensed and vaporized metallic states, and the approach at Dublin, where we consider everything to be incompressible and we don't explicitly account for the transition between metal and metal vapor, but to ensure that we are describing the right physics, we insert this recoil pressure term, a phenomenological recoil pressure term that gives a force at the interface due to going above the vaporization temperature. So both approaches have been validated heavily. So both approaches solve a momentum transport equation with terms for surface tension, Marangoni flow, buoyancy with a Boson-esque approximation, and a solidification source term, so a Darcy source term to basically force the momentum to be zero following solidification. Both approaches solve an energy transport equation with a heat input and latent heat terms due to melting, solidification and vaporization and condensation. Both approaches, as I say, have been validated using the common gallium melting case and the Sennen-Davies Marangoni flow case. The approach at Manchester we validated against this bubble growth, the superheated bubble growth case. And another difference, is that the approach at Manchester we've used mules to solve the volume fraction transport equations, and Galvin's approach uses isoadvector. So probably better description of the interface actually using Galvin's approach is fair to say, due to the smaller magnitude spurious currents when we're looking at lower length scale phenomena. Just a few more details. So obviously, because we're at Manchester, we're explicitly accounting for the transition between condensed metallic states and vaporized states. So there's a density change associated with that. So the divergence of the velocity field is not zero then, because when you derive these equations, you'll get material derivative of density. So you'll find that the divergence of your velocity field equals think it's -1 over the density multiplied by the material derivative of density. Yeah, that's when you expand this term out, actually you'll get something like that in your mules source term. And then that then also goes in your, so instead of projecting the velocity field to be divergence free, you project your velocity field to be divergence free minus this material derivative of density term, which is captured in this v dot term here. So, but otherwise, as I say, the physics, both models of capturing is the same, but just different approaches to represent that vaporization. So yeah, so here's just showing when you expand these terms what divergence of the velocity field should be, and how these volume fraction transport equations are implemented in mules. And here we're just showing that the volume fraction equations that we implement at Manchester, they do reproduce the mass continuity equation, which is obviously really important for any continuum mechanics description that we conserve mass. So in order to compare the two approaches then, in this work, I've simplified the approach that we've got at Manchester to just be 3 phases, so metal, vapor, and the gas phase, as opposed to what Gauderman's simulating, which is a metal and a gas phase. So as I say, just to clarify, we have this state transition between metal and metal vapor over the vaporization temperature with the rate term m dot. And we assume that the vapor phase is 1,000 times less dense than the metal phase, so that's how we get this recoil term in our approach at Manchester, due to that density difference, and we account for that volumetric dilation and constriction then on condensation. But just to let you know, there is a third approach, which is arguably, well, is the most highly cited approach in the literature by Chinapat Panwisawis, which is interesting because they consider their domain to be, again, 2 phases, similar to Gauderman's approach, but they have this above the vaporization temperature. They transform their liquid metal to the metal vapor, but they don't account for the volumetric dilation, so they still have div u equals 0. So their approach isn't mass conservative, but they've obviously had great success in their literature, even though it's not mass conservative. So that's just another approach to be aware of, sort of rightly or wrongly, got a lot of attention. So just a direct comparison then of the two approaches. So our approach at Manchester is shown in this green box, and the UCD approach by Gauderman Paravendran is shown in this red box. So yeah, it's quite interesting really. So the approach at Manchester, you can see the vapor plume. As I say, we explicitly solve for the vapor transition. So above the vaporization temperature, transform this alpha metal to alpha vapor. That has an associated material derivative of density that then goes into our pressure equation, as I said, to project that velocity field to, instead of being divergence free, to be basically equivalent to 1 over the density multiplied by the material derivative of the mixture density. So that's how you can see this sort of quite massive increase in what would be the metallic to overall metallic volume fraction, because the vapor is 1,000 times less dense. And in Gauderman's approach, obviously we don't explicitly solve for that vaporization, the alpha vapor. So Gauderman doesn't predict obviously this vapor plume, but what you can see is that the keyhole dynamics in terms of the liquid metal and the solid metal substrate are actually very comparable. So the progression rate of the keyhole through the substrate is pretty much exactly the same, and the volume of liquid metal around the top of the keyhole, this crown, is roughly the same. The topology of that is different between the two approaches, but that's because the velocity profiles that we're predicting at our approach in Manchester is quite different. So because we have this material derivative of density, we're predicting much higher velocity fields. So I can show you now the velocity field at 0.001 seconds for the two approaches. So at Manchester, we're predicting a velocity field of roughly 150 meters per second, whereas in Gauderman's approach, the peak velocity is sort of 15 meters per second, so an order of magnitude difference in velocity there. It's interesting because what a common criticism of these thermal fluid dynamics approaches for advanced manufacturing power beam scenarios is that they don't accurately predict the velocity profiles in the keyhole, which are generally of the order of hundreds of meters per second. So looking at this, you'd probably say, for qualitatively, that the approach at Manchester probably is a better you know, it's better capturing those vapor plume dynamics. But the truth is, rarely in these processes are we too worried about the vapor plume dynamics. Obviously, Gauderman's approach is accurately predicting the liquid metal behavior, the keyholing progression rate behavior. So I guess the takeaway from this comparison is that if only you would want to consider this material derivative density type approach if your process is heavily dominated by the vapor dynamics. So probably if you're interested in an electron beam welding case where the flow is largely dominated by the vaporization behavior, then you'd want to use something where you consider that material derivative density. If not, if you're just looking at a powder beam process, or even if you're looking at an electron beam welding process, but you're not too worried about the sort of capturing all the violence inside the keyhole, then you'd want to use an approach where you consider things to be incompressible and you have a much more efficient solution. Because as I say, Gauderman's approach is sort of at least an order of magnitude quicker, more efficient in terms of computation compared to our approach at Manchester, probably largely due to the fact that we are considering much higher velocities in our domain. So obviously the current number is directly proportional to the velocity field, peak velocity field in the domain. So that's one of the main reasons. And also, if we add more chemical components to our model, because ours is n component model, that will again sort of exponentially increase the computational cost. So yeah, pros and cons of both. And just to show here, what I'm showing is that our approach at Manchester is mass conservative, as I've said. I always like to show this just to highlight that it's something's trustworthy, I guess, if you can show that you are mass conservative in your implementations. So yeah, other applications, I'm running out of time, so I'll skip over really, but both approaches are highly applicable to advanced manufacturing processes such as powder bed additive manufacturing. As I say, if your process is dominated by vaporization, then maybe you'd want to consider the material derivative of density. But as I say, both approaches are highly applicable to any of these scenarios. The takeaway points, then, if I could summarize, is that if you are after a very physics-based solution and you're not too worried about the vapor plume dynamics, then the approach developed at UCD by Gauderman Parvenden is excellent approach. Fully captures the keyholing progression rate, fully captures the liquid metal and solid metal behavior just as well, I guess I'd like to say, as the approach we developed at Manchester. But what we are predicting more of at Manchester then is this the massive velocities that you get in the because we're explicitly capturing that state transition between condensed metal and vaporized metal. So we're probably more accurately predicting the vapor dynamics and not relying on the phenomenological recoil pressure implementation. So maybe it's fair to say that if you want the absolute best physics you possibly can, you'd consider an approach where you account for this material derivative density, but then you have to pay a heavy computational cost for that. So you have to ask yourself if it's worth it. And if you just want if you want to predict accurately the liquid metal and solid metal behavior, probably the temperature fields, then the approach of Gauderman Parvenden is absolutely brilliant. So yeah, pros and cons of both. And again, sorry I've run over slightly, but sorry I can't be there. I might be there by the time I'm giving this, but Gauderman's there to answer any questions that you might have, and I'll try and be there as soon as possible, and I'll answer any questions by text if you do have any, and my emails should be available in the conference portal. So yeah, this is Gauderman here, and this is me on the left. It's my dog here. So thank you for your time, and yeah, I'll look forward to any questions. And thank you very much for having me. It's been an absolute pleasure being part of the workshop. So yeah, thank you very much.
Okay, as said, it's Mr. Gautham may be able to answer some of the questions. I haven't seen any yet, but if you can please post any questions you have on the live Q&A session. Thank you, Abdul. Yes, it's excellent work there. They can be directed to Gautham or to Tom when he arrives, I guess, or for that matter to the dog if you feel that might be more appropriate. And the next speaker is Robert Kaiser from University of Zagreb. So can we pass control of the session over to Robert?
Just a second. So I managed to share the screen. Okay. Does everybody sees everything?
I can see it fine. Yes, I should imagine everybody else can.
Thank you, Tabor, for the introduction. And as you mentioned, my name is Robert, and I'm going to do a short presentation about the development of a Eulerian multifluid model for evaporating liquid sprays. I know it's nowadays it's not popular to talk about the future of internal combustion technology, and mankind is still highly dependent on that technology, and a lot of money and effort is still being invested into the development of that. And to simplify the things, there are two main approaches in development of IC technology. And the first one deals with increasing the efficiency of such machines, and the second one deals with the development of new fuels. For both approaches, the numerical modeling part is really critical. This work is part of a larger project called Predictive Modeling and Experimental Validation of Multi-Component Dense Spray Dynamics. This project is a collaboration between the King Abdullah University of Science and Technology, University of Perugia, and University of Zagreb. The goal is to develop high-fidelity modeling and experimental capabilities to predict multi-component dense fuel sprays. University of Zagreb is, of course, collaborating on the modeling part of the project, and we are collaborating on two development tasks. The first task deals with the development of a DNS solver for spray atomization, and the second one deals with the development of a Euler-Euler multifluid solver. This presentation deals with the second task. Just a few highlights regarding the solver. So Euler-Euler multifluid. This is a multi-phase or a two-phase solver for polydispersed flows. So we have one continuous phase and the second phase, dispersed phase, and also the dispersed phase. Both the Euler-Euler part means that both phases, the continuous and the dispersed phase, are treated as interpenetrating continua. Therefore, they're both described in the Eulerian frame of reference. On the other side is the Lagrangian, which describes the polydispersed part in the Lagrangian reference, but this approach takes into account both phases as continuums. The polydispersed part means that the dispersed phase is allowed to vary in size. And for that, we are using the method of classes to discretize the dispersed elements into classes according to their diameter. So certain sizes of dispersed elements are classified as one class. The multifluid part means that the solver is generalized for an arbitrary number of dispersed element classes. And with this approach, each class and the continuous phase have their own individual momentum equations and phase continuity equations, but all phases, all fluids share the same mixture pressure. This image here shows an example of a grid. So this cell here contains the continuous phase described with the blue color, and the circles varying in size and color represent various dispersed elements. And you can see one cell can contain multiple different classes and multiple elements. Therefore, it's computationally much less expensive than the DNS approach, for example. Since we were developing the solver from scratch, we divided the development of the solver into multiple milestones. So first, we started with the development of a basic multifluid model. After that, we added interface for interfacial momentum transfer models, multi-phase turbulence modeling, after that breakup and coalescence functionality, and finally evaporation modeling. We wanted to test if the solver is behaving as expected after each larger development milestone. So at the beginning, we first simulated monodispersed bubbly flows, after that polydispersed bubbly flows, non-evaporating sprays, and finally evaporating sprays. All of these validations and verifications were published with papers. And at the beginning, we selected the bubbly flows because they are easier and much more experimental measurements, detailed experimental measurements is available for that kind of flows. Therefore, at the beginning, after the initial implementation of the basic multi-fluid model and after adding interfacial momentum transfer models and turbulence modeling, we have first performed the verification validation for monodispersed bubbly flows. After, when we were satisfied with the results, we added breakup and coalescence functionality, and we also upgraded a lot of interfacial momentum transfer models. And here, in a large vertical pipe, the air is radially injected into the water stream, and then we were behaving the behavior of bubble populations, and we got adequate behavior, and we were satisfied with the results. After that, we switched finally to spray modeling. First, non-evaporating sprays. We, of course, needed to change the breakup modeling, interfacial momentum transfer models, and we added advanced turbulence coupling models, which coupled the dispersed phase turbulence with the continuous phase turbulence. And we also added non-uniform classes functionality, so we can increase the density of classes in certain regions of the population. For this test case, we have used the spray A non-evaporating conditions. So the liquid fuel is injected into a pressurized vessel at 300 kelvins. There is no evaporation. And the left bottom image shows the comparison between the experimental measurements and the numerical results for the liquid penetration. And as you can see, the numerical results capture the physics quite well. The right image shows the comparison of the SMD curve, so southern mean diameter curve, in the streamwise direction. Again, the CFD solver captures the rapid decline in droplet sizes quite well. When we were satisfied with non-evaporating behavior, we started developing evaporation capability. And in order to do so, we needed to reformulate the solver for compressible flows due to large changes in temperature and chemical composition. There are significant changes in densities. We also added species transfer equations, energy equations, both for the droplet phases and the continuous phase. And to capture the complex thermal behavior of droplets, we have added a non-uniform, or better to say parabolic temperature profile within the droplets, and also the inner circulation occurring inside the moving droplets is taken into account using the effective thermal conductivity model. And this all leads to a successful evaporation model implementation. We are currently using the Abrazo S. Sirigano model. I don't know if I'm pronouncing the names correctly, probably not. Finally, evaporating test case. Again, spray A, but in this case for evaporating conditions. Liquid fuel is injected into a pressurized vessel at 900 kelvins. The liquid core disintegrates into smaller droplets, which then easily evaporate. The left bottom image shows the comparison of the liquid and vapor penetration. Again, blue lines give the liquid penetration, and the solver successfully predicts that after approximately 10 millimeters, the whole fuel evaporates. And the red lines give the vapor fuel penetration. And again, the solver correctly predicts the penetration. And if we compare the radial mixture fractions, so radial distribution of fuel vapor at 25 millimeters and 45 millimeters in the streamwise direction, we get these two plots. And again, the solver successfully predicted the distributions. Since the goal of the project is to capture the complex fuel behavior, so multi-component fuel behavior. We are currently developing multi-component functionality. In order to do so, we need to add transport equations for liquid species transport, and we need to generalize the evaporation model for multi-component evaporation. And there are also tips for transfer of liquid species transfer due to breakup and coalescence, which is a little bit complex. Just to give you a short summary, the goal of the project is to develop numerical tools for predicting dynamic behavior of modern fuels. I have shown you detailed testing of the solver for each development milestone. The last two test cases showed you that the solver successfully predicts the dynamic behavior of non-evaporating and evaporating sprays, but at the moment just for single component sprays. And we are currently implementing the multi-component part. I would just like to acknowledge the financial and technical support we get from the KAUST, and also the financial support from the Croatian Science Foundation is also greatly appreciated. Thank you, and if you have questions, please share.
Thank you very much, Robert. I was about to give you a 2-minute warning when you moved on to your conclusion slide, so beautifully timed.
I heard your audio, so I stepped up the speed.
Are there any questions for Robert? There's one comment more than anything else from Dragana here. Hello, I worked myself the approach and must say this is excellent work. Thanks for a nice presentation. Are there any actual questions? I do have one question myself. You've got these classes represented in different components in the flow. Are these different bubble diameters?
Yes, so I'm dividing the population in accordance with their diameter. So one diameter represents a range of droplets, bubbles, or particles.
What made you use that methodology rather than a hierarchy of different moments of the distribution?
I will be brutally honest. Here it was defined in my PhD project, so
that's as good a reason as any other.
Yeah.
Okay, well, we've got about, just before we start the next one, we've got 3 more minutes. I see a message from Tom Flint saying that he is now here to answer any questions. So are there any questions for Tom? There's one question, actually, I think it must be for Robert again, from Lionel Gammett. Are these specific developments made open source? Are they things that you'll be able to share then?
Yes, it's developed in FOAM extent, but since I'm currently doing intense development on the multi-component part, it's not yet ready for publishing, but we will probably publish the solver when I have done my PhD.
Thank you. I can see a hand up from Domenico. Do you have a question?
I do. Yes. You mentioned the influence of the turbulence modeling in your work. What turbulence models do you typically use, and how did you modify it in your work? Thank you.
So I'm using the standard K epsilon with correction from Pope, and of course you need to change the equation so you're able to implement it in a Eulerian multi-fluid model, but I haven't performed any magical source terms which are often just mentioned and not described. So I'm not having any spray interaction source terms or anything like that, just the standard K epsilon modified for the Eulerian multi-fluid model.
Okay, thank you very much.
Thank you, Robert, for that, and thank you, Tom, for your recorded presentation. Let's move on now to Tom's colleague, Gutherman. I don't know if that's correctly pronounced, but from University College Dublin. So over to you.
Yeah, good afternoon, everyone. I hope you can see the slides without any issues.
I can certainly see them.
Okay, thank you, Professor Tabel, for introducing me. And I'm Gautam Parivandan, and I am an IFOAM researcher based at UCD. And this work is done in collaboration with Dr. Flint from University of Manchester. So yeah, this is the overall outline of the talk. I'll give a brief description of the powder bed fusion process, especially the laser beam ones, and then briefly describe the numerical methods that we incorporated in the study, and share some of the results that we got, and yeah, the summary. So powder bed fusion process, most of us know what it is, but still I'll explain it shortly. It is an additive manufacturing technique where a laser beam is used to fuse powder particles together in a layer-wise method to form the entire component. It's a fairly new technology, and it still suffers from several issues like processability and repeatability, and that can compromise the quality of the product. And some of these mechanisms that they take place in a very short length and time scale, and are difficult to observe by experiments. And this is where we believe numerical methods can provide a better understanding of the process. And in our study, we modeled this in powder level. We consider the powder bed, the metal phase, to be a confirmation of powder particles rather than just a single continuous phase with no voids in it. And to do this, we use a discrete element method. It's a meshless method where the trajectories of each and every particle is calculated using Newton's law of motion. And we create these particles, let them settle on the powder bed, and these particle sizes are chosen such that they represent the actual raw powder used in the 3D printing. And once we have the powder data from discrete element method, the location and size of each and every particle is then transferred to a mesh in OpenFOAM. And that gives us the initial configuration for the OpenFOAM simulations, the laser processing, part of the PBF process. And what we get from that is something like this. And we get this melt track formed as a result of laser processing, which can then be validated with experiments. And before I share more of these simulation results, I'll just briefly describe the models that we used in this study. So we, for the fluid model, we used a modified Navier-Stokes equation, where we included the effects of buoyancy-driven flow using Bushnell's approximation. We have this momentum sink that drives the velocities of solid cells in the metal phase to 0. We also have several surface forces acting on the gas-metal interface. And these include forces due to surface tension, Marangoni convection, where the fluid tends to move away from the hot region to a colder one. We also have effects of recoil pressure. And for the recoil pressure, we used a phenomenological model. And the advantages and disadvantages of this were discussed by my colleague Tom in a couple of talks before me. And for the thermal model, we use Waller's method for describing the solidification and the melting. We include the laser source only at the top part of this powder bed, and we also have heat sinks as a result of radiation, convection, and the evaporation. And that's the relation we use for the evaporation cooling. So for modeling the PBF-LB, the custom solver that we developed at UCD, it uses a volume of fluid approach to model the two-phase system where the phases are metal and gas. And we use thermophysical properties of stainless steel 316L and argon, respectively. And as I said earlier, the laser source is applied just at the top of the powder particles. So if you have like multiple particles lying on one another, we have just the heat source applied at the top of these, and we use like a simple path tracing to do that. Then we run this model for different process parameters, and we check the influence of these. We were able to capture some of these melt pool defects that form the actual process as well. For example, if we take the same case that I shared in the previous slide, we were able to capture these Rayleigh-Plateau instabilities that result in the breakage of the melt pool with higher scanning speeds. We also captured some of these void formations as a result of the melt pool collapsing over the keyhole, and also incomplete melting of particles when there is insufficient energy density. And for the influence of process parameters, for instance, when we keep the laser power, the scanning speed constant, and we change the laser power, we of course reduce the energy density when we supply lower power, and that results in a thinner melt pool when compared to higher power. and also leads to incomplete melting of particles. And when we, for instance, keep the latest power constant and change the scanning speed, with the low scanning speed, we of course deliver more energy density, and that gives us a wider melt pool and also very uniform melt track along the well direction. But as we increase the speed of the laser beam, it results in more of these in Rayleigh plateau instabilities that I taught to you before, and also a lot of these incompletely melted particles. And why do we need this is that we need to decide what will be the optimum parameter for a particular task we have at hand. For example, if I decide to print a particle with a scanning speed of 1.5 meter per second, how do I decide on the power? So for example, if I choose 150 watt, it's not enough to completely melt these particles, and a lot of these substrate end up captured with, under the melt track. We also have keyholes formed as a result of the voids as a result of this keyhole formation, and the Rayleigh plateau instabilities as well. But when I increase the power, for example, I can eliminate the incomplete melting, for example, but we still have these voids. So we can run these models to check what will be the optimum process parameter where we can avoid the defects as much as possible. And of course, these models have to be validated. And for this, the experimental data was provided by fellow IFOAM researchers who are based at DCU. And we compared the melt pool profile, for example, dimension, with the optical microscopy results, and also with the height of the melt track with the brutal profiliometry data. And then what we notice is, like, a lot of these studies, they did not consider the shrinkage that happens during the solidification, and this has to be included and when we are validating the measurements. And this is something we included in the study recently, and this model predicts the residual stress and the shrinkage during solidification and the dimensions of the solidified melt track. The model was originally developed by Klopsa for PMMA, I believe, and this was expanded for salt cores by Schilling et al. And we primarily adopted Schilling's method for this approach, but we have a couple of differences with regards to Schilling's approach. For instance, Schilling, in his model, he uses a single phase in the entire domain, but we have the problem of this metal and gas interface, and how do we deal with that? And the other difference would be they start with the solidification directly, but we start with a completely solid metal phase, and we have to start with the melting and then the subsequent solidification. So, but the overall flow of the approach is pretty much same to the Schilling's approach. So we solve the melt pool formation and solidification using laser melt foam. That's the solver for the viewer solver that I discussed earlier. And during this, we also record the solidification time for each cell, that is the time at which each of the cells solidifies, and also the gradient of temperature at that instance of solidification. And we use this data to calculate this parameter called residual temperature. It's different from the actual physical temperature, and we capture this data, and that is used to solve the displacements in the solid phase. And when we solve for displacements in the residual stress pool, we do not actually solve for the entire domain, but rather we extract the cells that are just solid, completely solid, and we solve displacements only for those cells, and then we map these values back to the overall the complete domain. These are some of the preliminary results, and I thought we'll good to share these, and these have to be validated later. When we see the stress along the melt line, we see that the residual stresses increase with the increase in scanning speed, and that trend agrees with the literature. But also you can notice that with very high scanning speed of 1.5 meters per second, the residual stresses are low, and these partly because there's a lot of voids that have been captured here that tend to relax the residual stresses. All these defects are interlinked, and the influence of process parameters are also interlinked. So these modeling approaches can tell us a good way on, can provide a way to find the optimum process parameter for PBF processes. And as to summarize my work, we used the discrete element method, especially a model called raindrop model, to emulate the powder deposition during the PBF process. And we used the custom OpenFOAM solver based on FOAM to model these melt pool thermo and hydrodynamics. And these models have been validated with the experimental data. And we also studied the influence of various process parameters on the topology of the melt track. And the residual stresses and subsequent displacements have also been modeled. And we also believe that these data can be helpful for the microstructure evolution study, which was described yesterday by one of my colleagues, Daniel Dreelan, in his talk. Thank you. And just before I finish, I would like to thank Shilin et al. For sharing their work with us, and also personally would like to thank Dr. Kutovich for his assistance throughout my project. And those are the contact details of me and Dr. Flynn. And if you have any questions, please let me know. Thank you.
Thank you very much, Gautam. There seem to be, actually, there are now 3 questions for you. Obviously, you've been provoking a lot of thought here. I'll read them out. First one from somebody who wishes to be anonymous. Excellent talk, Mr. Paravendam. The residual stress prediction looks very interesting. Is the plastic deformation incorporated?
Not yet, actually. We do have to incorporate plastic deformation. That's something that we saw in the results. But for now, we assume linear elastic model, and this is a code in development, and we are aiming to include the plastic deformation in the future, near future, actually.
Excellent. Next question from Jaga Parvisalam. Hi, Gautam. Very excellent piece of work. 1, how did you insert the powder boundary condition? And 2, have you tried the enthalpy porosity technique for the solidification process?
Yeah, for the first question, we divide the domain into columns of cells, and we at each time step we check the top surface using algorithm to check the top surface using. We go through each of these columns and see the top surface using volume fraction of the metal, and just use like a switch value for these cells, and then we just multiply that with the laser power. And for the second question, I didn't actually try a lot the enthalpy porosity technique, but yeah, this is something I'll give it a thought.
Great. Another question here from Kaspara. What solver was used for the residual stress calculation?
The solver was it's mainly similar to elastic thermal solid foam in FOAM 4. I don't know if there is a version for other forts of OpenFOAM, but for FOAM it's elastic solid thermal foam. And the only difference is we have this extract mesh included in the solver.
Fantastic. Thank you very much for that. It's not a question, but it's a comment which I certainly agree with from Sal. A very interesting talk there. I think at this stage we are a minute ahead of ourselves, which is better than the reverse. So we will hand over to Domenico Lahaya from TU Delft, if you're there, please.
Yes, I'm here. Thank you very much.
Excellent.
I will share my screen.
Good. I can see your screen, certainly.
Thank you so much for that confirmation. And now you should see the full screen mode.
Not yet. I knew this session was going far too well to be.
Just a moment.
Take your time. Ah, that's looking good. That looks correct. Please take it away.
Thank you so much. I would like to thank the workshop organizers and the session chair for giving me the opportunity to give this presentation. I would like to talk about the modeling of turbulent non-permixed combustion in a single heating section of an non-baking furnace. This is work in which the University of Delft collaborates with the company Aruchemie in the harbor of Rotterdam and with two engineering firms. One is PM Squared Engineering and the other one is Creative Fields. This talk overlaps with the second talk in the session, both for the aspect of the combustion and the context with Zagreb. What is the topic of the presentation? We would like to model a bakery. A bakery not for bread or for pastries. What you see here is a factory of a firm in which blocks of anodes are being baked, and the baking takes place in these vertical holes you see in the picture, and the thin narrow strips are the furnaces, as I will explain you later on. What is the interest in doing the modeling of these furnaces? There are a variety of motivations. The factory is located in the harbor of Rotterdam. The harbor is in a location with a lot of housing and natural habitat that we like to protect from the pollutant emissions of the furnace. So the reduction of pollutants is one driver of the work. Another driver is the fact that, as mentioned before in the session, the use of hydrocarbon fuels is being challenged. There is the need to move away from these hydrocarbon fuels. I would like to understand how to do that in a best possible way. I will now focus into a detail of the furnace. The furnace consists of multiple sections and multiple rows of multiple sections. What you see here is a detailed view of one single section in which the temperature is highest among the different sections. Temperature being high means sensitive to pollutant emissions. Due to the high temperatures, nitric oxides are likely to be formed. The picture shows a double U shape through which the oxidizer flows from left to right, and it passes to this double U. From the top, there is two injection points of methane or natural gas. The natural gas and the oxidizer will mix, and a combustion will take place. Several questions will emerge. What is the temperature that will be the result of the combustion? How will the heat flow distribute through the gas domain? Flow from the gas domain through the wall into the material? And where are the emissions being formed? And what can we do in terms of measures to reduce the emission formation? one of the ways that the factory has in the past tried to reduce emissions is by investigating the way in which the fuel is injected into the furnace. So what you're seeing in this picture is a detailed view of a single fuel injection. So,
Domenico, we seem to be losing you, or at least I seem to have lost you. Hello?
I'm sorry for this interruption.
I'm afraid you're breaking. You've disappeared again. Your sound is very intermittent and it's non-existent now. Is there anything you can do about this, or is it anything to do with the conference? Ned?
Is the connection again established?
There's a comment from the conference helper here. If you want to turn your camera off, this might help since you've got a bit of a connection issue. I'm not sure that you aren't already switched off on your camera. Yeah. So your sound is very intermittent. If you haven't already, if you can switch your camera off, it might help.
Okay, I'll try to do so.
Yes. That's sounding better already.
So I switched off the camera in order to save bandwidth.
Mm-hmm.
I was coming to the challenges in the modeling of the furnace. And here I listed a few of the challenges that we have. We have a challenge in terms of flow, of the combustion of the flow in the furnace, because of the way that the furnace is being shaped, and also because small obstacles are being placed in the main channels to be able to have a uniform flow, therefore uniform combustion and heat release. The fact that we have two fuel inlets results in a staged combustion process. So therefore, we have a change of oxidizer composition as the oxidizer moves from the first to the second fuel jet. This imposes challenges in terms of the combustion model and the chemistry used for the fuel. And we have challenges in terms of indirect heating. That is, how does the heat distribute in the gas domain and goes from the gas domain into the solid walls and to the material being baked. So these challenges motivate trying to do the modeling of the furnace. I will show you here sample results. These results are in a preliminary stage as the The simulations are still ongoing to obtain a better converged results. However, what I will show already gives you the idea of what we are trying to achieve. You see here on the left the inflow of natural gas, the left and right jet of natural gas, and on the right the flow of the fuel, of the oxidizer. And you see that in the right picture the oxidizer is being consumed as it flows through the furnace. As the combustion goes on, temperature is being formed, and it goes from the gas domain into the solid domain through the wall by a radiator flux through the wall. And what you see over here is how the flames being formed underneath the fuel jet cause heat to flow into the lining of the furnace. I will now talk about the mesh generation. Given that the geometry is not a trivial geometry, we are confronted with the challenge of mesh generation. Here you see a view on the global mesh. And the next slide gives you a detailed view on sections of the domain. The view on the left gives you a detailed view underneath the first fuel jet and a bit towards the right. The picture on the right gives you a view on the bottom left of the furnace, where you see how the obstacles are being refined circumferentially to be able to capture the boundary layers.
Just to say, Domenico, you've got 2 minutes left on the presentation. We won't take any questions here, but you might want to take this into account in terms of what you present from now onwards.
Thank you so much. And we're also able to compute the skewness of the mesh. Very briefly, given time, we're able to model the turbulent flow, we're able to model the chemical reactions, and we're able to model the radiative heat transfer in the gas domain into the solid. We do that by using CHT multi-region foam with different settings. We hope to present results in the full paper with more detail. To conclude, we model a combustion process in a section of a ring furnace to be able to meet requirements on the environmental and productivity constraints. And the model gives more insight, more than before, into how flow, heat release, and pollutant formation develops in the furnace. And the last slide gives you some references on the work. I'd like to thank you very much for your attention.
Thank you very much, Domenico. I remind everybody that, of course, the abstracts are available on the online platform here. So if you want to look through anything there, that's a good way of doing it. And I guess, Domenico, will probably be around for the rest of the conference. So if people want to ask you questions, I'm sure there are ways of doing that through the platform. And I'd really just like to thank all of the speakers for their very interesting presentations. It's been a great afternoon session, and to remind you all that there is I believe the next thing is the musical session in about 30 seconds time here. So I look forward to seeing you in other sessions later on in the conference. And my thanks to the session organisers who have helped take this session forwards. Goodbye, everybody.